All right, welcome back to Honors Calculus. In this video, we're going to be looking at graphing functions. More specifically, we're going to be looking at summarizing all of the tools and techniques that we've talked about in the last several videos and bringing them together and seeing how we can use calculus to better graph functions that we don't necessarily understand on their own. All right, so let me get my head out of the way and let's think about all of the tools that we have for graphing a function. We can look at the axis-intercepts. We can look at discontinuities. When you have a piecewise defined function, sometimes that means that there's going to be a different value on the left and on the right. We can take care of that using limits. When it is a single function, that very often a discontinuity means a vertical asymptote. We can look at the limiting value to determine if that's actually what's going to happen. And we can think about the behavior going towards that asymptote from one side or the other. We can think about horizontal asymptotes. Sometimes those are important tools, sometimes they are not going to show up, but we can think about them. We can also think about slant or skew asymptotes, which sometimes can be a thing, but we're not going to worry about just for the sake of time here. We can think about the extrema. We can think about increasing and decreasing ranges, but the extrema generally handles all of that for us, so we don't have to think about it separately. And then finally, we can think about the concavity and the points of inflection. We can bring all of these things together in one place in order to try to analyze the graph of a function as a cohesive whole. All right, so let's take a look at this function. F of x equals x squared minus 2x plus 4 all over x minus 2. And looking at our list, the first thing I suggested looking for were the axis-intercepts. The intercepts, of course, we have a y-intercept. That's the easiest thing to evaluate of everything on the list. Plug in that x is equal to 0, and we get 4 over negative 2, which is negative 2. So 0, negative 2 is an axis-intercept. Then we can set the function equal to 0. X squared minus 2x plus 4 all over x minus 2 is equal to 0. Multiply both sides of the equation by x equals 2, and as long as x is not 2, we get that x squared minus 2x plus 4 is equal to 0. I can't think of any pair of numbers that multiply to 4 and add to negative 2. So I guess I can go to the quadratic formula. X is equal to the opposite of b. Opposite of negative 2 is positive 2, plus or minus the square root of b, which is negative 2 squared. That's 4. Minus 4 times 1 times 4, that's 16. All over 2 times 1, which is 2. But I get here that the discriminant is negative 12, which is less than 0, which means we have complex roots. We could solve and find the values of those complex roots if we thought it would be useful, but we're talking about graphing. So we're looking for points on a number line, and complex roots definitely do not appear on a real number line. So no other intercepts. We're done with that. The next thing we want to think about are discontinuities, places that might be vertical asymptotes for that matter. And here we have a rational function that we're looking at, x squared minus 2x plus 4 all over x minus 2. And we know that the discontinuities of a rational function occur when the denominator is equal to 0. So we know that there's going to be a discontinuity when x is equal to 2. And if we consider in the limit as x goes to 2 of x squared minus 2x plus 4 all over x minus 2. Well, plugging in x equals 2 here, we'll get 4 minus 4 plus 4, which is 4 over 0 undefined, which means that this is actually going to go to positive or negative infinity. I don't know which one it's going to be, but maybe I can figure that out. What I do know is that x equals 2 is a vertical asymptote. Right. The next thing that I listed was a horizontal asymptote. This is a rational function. It has no square roots, so I know that the asymptotes are going to be symmetric. That makes my life a lot easier. So I'm just going to take a look at the limit as x goes to positive infinity. I'm never going to look at negative infinity. I guess before I do that, I should put in a heading and say that this is a check for horizontal asymptotes. All right, so we're going to look at the limit as x goes to infinity of x squared minus 2x plus 4 all over x minus 2. And if we tested that right away, we'd find that it was a infinity over infinity, which is an indeterminate form, which means that we need to simplify. All right, so it's going to be 1 minus 2 over x plus 4 over x squared all over 1 over x minus 2 over x squared. All right. And the important thing there is that we are not going to get a horizontal asymptote either. All right, so what do we know so far? We know that the point 0, I'm sorry, not 0, 2. We know that the point 0, negative 2 is the y-intercept of this function. We know that x equals 2 is a vertical asymptote. We know that there is no horizontal asymptote, and we know that there is no x-intercept. The fact that we know that there is no x-intercept and that there's no horizontal asymptote actually gives us a lot of information, because we know that in order to get through this point and go towards this asymptote, that we have to go downward. And we know, because there's no horizontal asymptote and there's nothing else, that we're going to have to go downward this way. The problem is that we don't know exactly what that's going to look like yet, because we don't know where the turnaround happens. It could be that it actually is that simple, or it could be that something more happens, right? It could be that this function is going to end up looking like this and having a turnaround, and then looking like this and that before it has a turnaround. Those are perfectly reasonable things for the function to do. In order to figure out which, if any of those things actually happens, we can continue onward and start looking at extrema and concavity. All right, so because we have the first derivative test and the second derivative test, and we're also going to be looking for concavity anyway, I'm going to look for critical values. I'm not going to test to determine if they are actually extrema or not. I'm just going to list out all of my critical values. So remember my original function, f of x is x squared minus 2x plus 4 all over x minus 2. And I can differentiate that, f prime of x. Well, we'll have the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over denominator squared. All right, multiply some things out. I find that since I don't have anything else going on, let's distribute that subtraction to make sure I don't make any stupid mistakes. 2x squared minus x squared is x squared. Minus 4x plus 2x is minus 2x. Oh, and there's another minus 2x that I didn't simplify yet. So we've got minus 4, minus 2, and plus 2, which all told is minus 4x. Then we have plus 4 and minus 4, which cancel each other out. All right, the critical values occur when the function is either, or when the derivative is either 0 or undefined. Which means that either the numerator or the denominator of the fraction is equal to 0. When the denominator is equal to 0, we get that x is equal to 2, which is already a vertical asymptote, and asymptotes cannot be extrema. But we know that that's a point that's going to be of some interest to us. X squared minus 4x equals 0. We can factor that's going to be x times x minus 4, which means that either x is 0 or x is 4. We've already plotted x equals 0. That was the point 0, negative 2. So the point x equals 4 is the only point that we haven't plotted yet. It may or may not be an extreme value, but let's go ahead and plot it anyway. F of 4 is going to be, well, x is 4 squared minus 2 times 4 plus 4 all over x, which is 4 minus 2. All right, so it's 16 minus 8, which is 8, plus 4, which is 12. 12 over 2 is 6. All right, so 4, 6 is a point on the curve. We can try to remember that. Whether or not that is actually an extreme value, it's still a point that we can plot, and that might help us out. All right, the last thing to look for is concavity or points of inflection. All right, to find that, we're going to need the second derivative. So let me go up the screen a little bit. and steal f prime of x so that we can differentiate it. All right, so derivative of numerator times denominator. Actually, this is probably going to be a little bit easier if I remember that x minus 2, the whole thing squared, is x squared minus 4x plus 4. So that when I take derivative of the numerator, that's 2x minus 4 times denominator, that's x squared minus 4x plus 4, minus numerator, x squared minus 4x times the derivative of the denominator, which is going to be 2x minus 4. And that whole thing is going to be over denominator squared, x minus 2 squared. Squared is x minus 2 to the 4th power. All right, so using either the factored or the expanded version of that denominator as is useful. When I have to take the derivative, I might as well use the expanded form. That makes life easier. When I have to square it and then factor to see if something will reduce later, I'll take the collapsed form. It's easier. All right, let's multiply some stuff out. Or I could get a little bit cute on this, but I think I'll just multiply everything out and deal with it from there. No, that's stupid. I'm going to get cute with this because I can. I don't know. 2x times x squared is 2x cubed. 2x times minus 4x is minus 8x squared. Then we have minus 4 times x squared, which is minus 4x squared. We'll have 2x times 4, which is 8x. We will have minus 4 times minus 4x, which is plus 16x. We'll have minus 4 times plus 4, which is minus 16. Expanding out the other one, we'll have x squared times 2x, which is 2x cubed. We'll have x squared times minus 4, which is minus 4x squared. We'll have minus 4 times 2x, which is minus 8x squared. And we'll have minus 4x times minus 4, which is plus 16x. All right, notice here, we've got a 2x cubed minus 2x cubed, which cancel out. We've got a minus 8x squared minus 8x squared, which cancel each other out. We've got minus 4x squared minus 4x squared, which cancel each other out. And we've got 16x minus 16x to cancel each other out. You could have noticed before multiplying everything out that there was a common factor of x minus 2 that could be pulled out of the whole thing. If you had done so, you would have reduced the fraction early, and the writing it out would have been a little bit neater, but it would have required a lot of thought and a lot of care in factoring. So I don't know if one way or the other is easier. But regardless, we get that the second derivative is 8 over x minus 2, the whole thing cubed. Notice that this is never equal to 0, so there are no points of inflection. But it is undefined when x is equal to 2. And so that split at x equals 2. Everything smaller than 2, well, then x minus 2 is going to be negative. Cube it, it's still going to be negative. 8 divided by a negative is negative. Anything bigger than 2, x minus 2 is going to be positive. Cube it, it's positive. 8 divided by something positive is something positive. So we know that we are going to be concave down everywhere to the left of x equals 2, and we're going to be concave up everywhere to the right of x equals 2. I'll remind you from our previous discussion, we saw that x equals 0 and x equals 4 were the critical values. When x equals 0, we are concave down, and when we're concave down, that means we might have a maximum. When x equals 4, we're concave up, and when we're concave up, that means that we have a minimum. And now we have all the tools that we need. To finish our graph. We had previously the one intercept, we had the one vertical asymptote, and we discovered the one additional point in question. We know that there is no x-intercept and there is no horizontal asymptote. And actually with that, we have everything we need in order to graph this. Because we know that we have a minimum here and we have a vertical asymptote here. The only way to get a vertical asymptote from a minimum is to go upward. We also know that this is concave up the whole way. And then we're going to have to go upward again, and there's nowhere to turn around. So that gives us our end behavior as well. We get something that looks like that. Likewise, the other point that we have, x equals 0, we know is a maximum, which means that the only thing we can do is just go straight downward. Something kind of like that. We could go back and analyze the limits at infinity a little bit more and see if we could figure out a little bit more about how the end behavior works. In this particular case, we're going to have a slant or oblique asymptote, but that's a little bit more than I really care about. And so I'm going to wrap this problem up with just that. We've established the graph, we've established where the extrema are, we've established what the concavity looks like. That's enough information for me. All right, so instead, let me scroll the page a little bit. Let me give you one to try on your own. All right, I would like you to take a look at the function y equals the square root of x squared minus 5x plus 4 . And again, I know that you could just go into Desmos or something like that, type in the equation, and it would plot out everything that you need to know here without you having to even think about it. That's not obviously what I'm looking for. I want you to analyze what the intercepts look like. I want you to analyze what the extrema looks like. I want you to analyze the concavity, any asymptotes that might be occurring. Go through that whole process and see what you end up with on this one. See what you can do. I'll see you in the next video.